Okay, hello everyone again. As promised, I'm going to do a short lesson on NMR. There are things about NMR that you need to know. There are at least 4 one-marker NMR questions. One of them is that for standardization or internal standard, remember you need to use tetramethyl silane. And tetramethyl silane, which is this thing, silicon CH3 4 times, has 12 identical protons that appear in ppm 0. And it is basically used for calibration of the machine, and if that goes on ppm 0, then it means everything else would be read correctly as well. The other thing you need to know, so that's internal standard. They usually give you 1 mark for that. In which region of the electromagnetic wavelength do we use as a source of energy? That would be low energy radio frequency. If your sample is liquid, well, you just put it in the quartz test tubes, special test tubes for the NMR machine, and that would be that. But what if it is a solid? Then you have to obviously dissolve it in a solvent, and the solvent must be deuterated. It must not have any protons, because if it has protons, of course, it will show up on the NMR. So, for example, you cannot use CHCl3. You have to use CdCl3. Or if your sample, for example, is if your solute is nonpolar, then of course you have to use a nonpolar solvent, something like that. A solvent that does not have any protons in it, any hydrogen in it. So TMS, low energy, and tetramethyl silane, low radio frequency, and using deuterated or solvents that do not have any protons. Another potential 1 marker is when do we use deuterium oxide? You see, if you have a compound that has an OH or maybe NH sticking, as a functional group, if you use deuterium oxide, deuterium will go and basically displace proton with deuterium. And then the signals, if they were there, they will disappear. All right? So the use of deuterium oxide, the use of deuterated solvents or solvents without any protons, radio frequency as a source of energy, and also internal standard tetramethyl silane. Each of these, when asked, they probably, if I can tick them off, 1 mark each. All right, so this is before we actually do the analysis. I hope that is clear. Now, let's try to see that if we had something like this, I don't know, I'm just writing something random, CO, CH2, CH3, let's put a CH3 there as well, just for fun. Well, how would this look like on an NMR? Well, what I'm about to tell you is you do not need to memorize the actual positions where these signals appear, because they're all on your data sheet. But what I always tell all my students is, how do the signals appear? How do they appear? And where do they appear? Now, let's plot the entire spectrum going from 0 to 12 ppm. Let's try to do the scale correct. So 3 there, and 9 there, and therefore you have 1 and 2, and 4 and 5, 7 and 8, 10 and 11. Okay, now if you've got something like this, where would you see the signals and why? Okay, I hope you understand the how and the where, and then the other one is how many. By how many, I mean how many protons are there in that signal. Let me get rid of these because I need this space to actually do the analysis. Now, let's use different colors for each of these things. Let's start from that end. Where does that CH3 appear? CH3 is sitting next to an alkyl. Bear that in mind. CH3 is sitting next to an alkyl. Where do alkyls appear? In the 0 to 2 ppm. Again, I reiterate, I perhaps know these things from by heart. You don't need to. You have to refer to the data sheet. So its neighbor is pulling it towards the 0 to 2 region. So that's where the CH3 will be. But how does it appear? Well, how it appears is again to do with its neighbor. Its neighbor has got 2 protons, and therefore it will appear as a triplet. Do you remember the n+1 rule? If I may go back, just the n+1 rule. So if your neighbor has 2 protons, you will appear as a triplet, because 2 protons generate 3 different magnetic environments. So the CH3 is going to appear here. Let's put it here as a triplet. The number of protons is 3, and 0 to 2, because his neighbor is an alkyl. All right, let's change the color. Let's move to this one. CH2. So where do you appear? Well, on my right side, I have an alkyl trying to push me in the 0 to 2 region. But on this side is oxygen. And if you are directly attached to oxygen, oxygen pushes you to 3 to 4 region. And because 3 to 4 is higher than 0 to 2, then therefore this guy goes in the 3 to 4 region here. All right, so we know where. But how? Well, this side doesn't have any proton, but that side has 3 protons. So that CH2 is going to appear as a quartet in the 3 to 4 region. And the size of the signal, as you can see, is proportional to the number of protons. So I do that there, and let's, if we color code this, then you can follow this later much better. Let's change the color to something different. Obviously, this is not a proton. That does not have any proton. And then you come to CH2. CH2 on one side is attached to a carbonyl, and on the other side is attached to an aromatic system. When you are attached to either a carbonyl or an aromatic system, you are pushed in the 2 to 3 region. Again, you can see that on a data sheet very, very clearly. So in the 2 to 3 region, but neither that carbon nor that carbon over there have any protons. So its neighbors don't have any protons at all. So it is going to appear as a singlet, because his neighbors are not going to generate any different magnetic environments. So where does it appear? I mean, both of these guys on either side of CH2 are pushing it towards the 2 to 3 region, which is here. And then, of course, it will be a singlet. Because its neighbors simply don't have any protons. And then you come to the protons of an aromatic system. Usually on your exam papers, they write them as that, with not showing any protons. But remember, that one, that one, that one, and that one have protons. So where do the protons of an aromatic system appear? Again, if you check your data sheet, you'll see that they will be around about 6.8 to 8.2. And usually they appear around about 7-ish. And usually they appear with a very disturbed base that we totally ignore And the reason that there is a disturbed base is because these protons, to be honest with you, are not identical, are they? But as far as the A-level exam is concerned, they totally ignore that, and you just consider that as a singlet. But the number on top is enormously important. Why? Because if, for example, you've got 4, it means you have a di-substituted aromatic system. I mean, benzene has 6 protons, doesn't it? But if you read that it's got 4 protons, it means in 2 positions it's been substituted. So any of these protons, right, that I'm drawing in brown are there. And then we come to that methyl functional group that is sitting on the aromatic system. As I said earlier, if you have an alkyl system on an aromatic system, anything attached to the aromatic system is pushed in the 2-3 region, ppm. It's pushed to 3-3. But the thing is, the carbon that is attached to, to the methyl functional group doesn't have any proton. So again, that is going to appear as a singlet in the 2-3 region as well. So you have another one in the 2-3 region. Let's draw it in a different color. No, not this color. We've already used that. Let's use another color. Yeah, something like that. And then you have another 2 over there. And then that's that. So that is as far as the proton NMR is concerned. Analysis of these. Usually what you have is this. You have to come up with that. And the explanation is the reverse of what I've just been telling you. You have to construct a nice table. You have to say, where is it appearing and how is it appearing and how many protons there are. And for each of those, if you get the rows correct, you get 1 mark. Now you might be thinking that if that CH3 was sitting over here, you would still have the same NMR. But you wouldn't be the same isomer. And that's where carbon-13 comes in handy. So what does carbon-13? So you probably might be given a carbon-13 spectrum with a certain lines, number of lines coming out from it, yeah? Now, this is the way I've drawn it is an asymmetrical molecule. It means every one of these carbons are sitting in a unique position. So 1, 2, 3, 4, and then there are 6 here, 10, and that's 11. So as far as carbon-13 is concerned, there are 11 signals here, right, for this particular one. Now, imagine if that CH3 was actually here. I write if, right? Then what would be the situation? Try not to see this anymore. But now can you see that the molecule is going to be symmetrical about there? Which means these 2 and these 2 are going to be identical carbons. So you will have your carbon-13 with only 9 signals. And that way you can tell which isomer it is, which is also part of the deal as far as NMR analysis is concerned. So to recap, where are the signals? The neighbor. Is it directly attached to oxygen, to carbonyl, to aromatic system? What is it attached to? And all of that information is on your data sheet, right? And then how they appear also says something about the neighbor. You see, when you have a triplet, it means I'm sitting next to CH2. It's blatantly obvious now. And if you're a quartet, it means my neighbor is a CH3, right? Now, the other scenario is that you could be, let's write this a little bit clearer. You could be CH2, CH2 on that side and CH3 on the other side. So how does this guy appear as? That one over there. Well, the total number of protons on either side is 5. So this is going to appear as, 2, 3, 4, 5, 6. N+1 rule. And the reason that they peak like that and drop like that I don't think you actually need that for the example, but just for the sake of argument, if you're CH2, if you're CH2, why does your neighbor appear as a triplet? Because if there are 2 protons, if this is the external magnetic field, in one probability, both of them could be parallel to the external magnetic field. There is a probability that the first one could be parallel, the second one against, or the first one against, the second one parallel. There are 2 possibilities there. And then the other possibility is that both protons would be spinning against the external magnetic field, and there is only one probability there. And that's why the signals look like a bit larger in the middle and 2 small ones on either side. It's all due to probability. And we can do the same thing for CH3 as well, but that would take much longer time. You understand? So that's how the signals look the way that they do. So again, we go back to this. Just try to listen maybe a few times as to how I was explaining this. But this time around, when you look at it and when you listen into it, imagine you're given the spectrograph and you have to come up with that, whether it is based on 11 carbon 13 signals or 9 carbon 13 signals. Okay? I think that would do for now. Thank you.